Hi everyone! In this video, we'll learn how to calculate binding energy in units of MeV per nucleon. Our goal is to calculate binding energy, but first let's define it. Binding energy is the energy that binds the nucleons, the protons and neutrons, together in the nucleus. Another way we can think about it is as the energy required to break apart the nucleus into its nucleons. If we look at this binding energy curve of MeV per nucleon as a function of isotope mass number, we see that it peaks at a mass around 60 units. Binding energy is one measure of nuclide stability. And the higher the binding energy per nucleon, the more stable the nuclide is. I'm not going to lie, binding energy calculations can be tedious. There are a lot of steps with a lot of digits, which leads to a lot of places where we can make mistakes. But let's start with a simplified, less scary version of what we need to do. Then we'll look at all the details. I think it's useful to keep in mind that we have three general steps. First, we need the mass defect. If it's not given directly in the problem, then we'll need to calculate it. Then we can use the mass defect to calculate the binding energy per nucleus. And finally, we can convert that binding energy to units of per nucleon. Now we'll look at the details of each of those three parts, starting with how to calculate mass defect. It turns out that the mass of the nucleus is less than the mass of the individual nucleons. This difference in mass is the mass defect, delta M, which equals the mass of the individual nucleons minus the mass of the nucleus. So how do we calculate it? First, we need to know how many particles are in the isotope of interest. This is the easy part of the calculation. We'll only consider neutral isotopes, and we can get the number of protons and number of electrons from atomic number Z, right off the periodic table. The number of neutrons must be calculated as mass number minus atomic number. Then we need our two parts to calculate delta M, mass of nucleons and mass of nucleus. The mass of the nucleons we get by adding together the total proton mass and the total neutron mass. We get each particle's mass contribution by multiplying the number of particles by the mass of the particle. Then we need the mass of the nucleus. If this is provided directly in the problem, great. Otherwise, we need to calculate it as the measured atomic mass minus the total mass of the electrons. Make sure you're using the measured atomic mass in this step and not the nominal value from the mass number A. Finally, we can calculate delta M because now we have both parts, the mass of the nucleons and the mass of the nucleus. After subtraction, the mass defect, delta M, will be a positive value. The next part is to convert mass defect to binding energy. Our specific example in this video is to end up with units of MeV per nucleon. The easiest way to do this calculation is to have delta M in units of unified atomic mass units, or U, because then we can apply a one-step conversion which relates mass in U to energy in MeV, or mega electron volts. When we do this calculation, our units end up as MeV per nucleus because the mass defect was for the nucleus. Our final step is to get this energy in units of MeV per nucleon, which basically means dividing by the number of nucleons. I recommend that you set this up as a conversion factor so units cancel, where one nucleus equals the number of nucleons. The mass number A is the total number of nucleons in the nucleus. Okay, one more thing before we work on the example. We'll need data. The measured atomic mass should be provided in the problem. I used the measured masses from the 2020 atomic mass evaluation. We'll also need the particle masses, they're listed here in U, and the energy equivalent in MeV. These are all 2022 CODATA values which come from the Committee on Data of the International Science Council. I think it's important for you to know that these are measured values, and the international community updates them periodically based on new measurements. I strive to use updated data in all my examples and cite the sources of those data. Unfortunately, many textbooks, even pricey commercial ones, and internet resources don't cite their sources, making it difficult to track which data they use or the accuracy of those data. As a result, you'll find many different values out there depending on where you look. Okay, let's work on our example. The first thing we need is to know how many particles of each type we have. And we can see here from the isotope notation for neon 22 that it has atomic number 10. So we have 10 protons and 10 electrons. We need to calculate the number of neutrons, and we're going to do that directly on the symbol. So we subtract, this is a little trick, A minus Z, so 22 minus 10 gives us 12. So we have 12 neutrons. Now we need to calculate the contribution in mass from each particle, the protons and the neutrons. And I'll go ahead and start with protons. So for protons, I have 10 times the mass of the proton, 1.007276467. And when we multiply those together, 10 times 1.007276467, rounded to 10 digits, gives us 10.0727647, and the units are U. We'll do a similar calculation for our neutrons. We have 12 neutrons times the neutron mass, which is 1.008664916. And when we do this math, 12 times 1.008664916, we get 12.10397899 U. To get the mass of the nucleons, we add those values together. We have 10.007276467 plus 12.10397899, and that gives us 22.17674366 U. Our next step is to calculate the mass of the nucleus. We have the measured atomic mass given in the problem. We need to subtract the mass of the electrons. So we're going to do a similar calculation with the electrons as we did with the protons and neutrons. We have 10 electrons. The electron mass is 5.485799909 times 10 to the negative 4. When we multiply those together, 10 times 5.485799909 times 10 to the negative 4, rounded to 10 digits for consistency, and I'll go ahead and put this in decimal notation, we get 0.005485799 U. So the mass of our nucleus will be the atomic mass given 21.991385511 minus the mass of the electrons 0.005485799. Doing that math, 21.991385511 minus 0.005485799 gives us 21.98589931U. So again, I've kept 10 digits, which is the limit of my calculator, for all of these calculations. Now, when I go to calculate delta M, I'm going to round that to 5 sig figs just for simplicity moving forward. So delta M, which must be positive, so that means we have to take the larger minus the smaller, which will always be nucleons minus nucleus, 22.1767436 minus 21.98589931. Doing the math, 22.1767436 minus 21.98589931, and that gives us 0.19084 U per nucleus for our delta M. I think you can see what I was talking about when I said these calculations can be tedious and there are lots of places where mistakes can happen. The next parts are a little bit easier. So now we're going to take our mass defect, apply the conversion, and that will give us binding energy per nucleus. I do strongly recommend that you write this all out, conversion factors, units, everything, so that way units cancel and it's just one additional check as you're doing these calculations. So now for binding energy, start with my delta M. Now I'm going to write it like this, 0.19084 U per nucleus. Now I'm going to apply my mass energy equivalence. I need to make sure that the units cancel. So that means 1 U will be in the denominator and 931.494104 MeV goes at the top. So U will cancel, and you can see that we'll be left with units of MeV per nucleus. Now we rounded our delta M for convenience to 5 sig figs. It's still a measured value and we still have to keep track of our sig figs moving forward. So we have 5 sig figs in the delta M and 9 sig figs in our mass energy equivalence. It's not exact. So our binding energy at this point will end up having 5 sig figs. So doing the math, 0.19084 times 931.494104 rounded to 5 sig figs gives us 177.77 units of MeV per nucleus. We're almost there. One more step, and that is to do that conversion from per nucleus to per nucleon. Remember, the number of nucleons is equal to the mass number, so we have 22 nucleons. So we're going to set this up carefully. So now I'm starting with my binding energy, 177.77 MeV per nucleus. And then I apply my nucleons. So 1 nucleus goes at the top, so those units will cancel, divided by 22 nucleons. Nucleus will cancel, And now we can take a look at our sig figs. We still have 5 sig figs in our binding energy. Nucleons are exact because it's a counted number. So our final result will be rounded to 5 sig figs because we ignore exact numbers. So our final calculation, 177.77 divided by 22, rounded to 5 sig figs, gives us 8.0805 units of MeV per nucleon.